Everyone, it's Dr. Fox here again. This is lesson 1 in a series on the thermal physics unit of the AQA A-level physics course. It's 4 lessons. They're quite big lessons, but they all sort of like merge into each other. And the reason I put this particular one together is that exam questions always involve all of this. You don't get particularly ones. You get latent heat and you get specific heat, and the first law of thermodynamics all sort of rolled in together. And that's why I'm going to do it all together, give you a couple of examples at the end. And please stop the video and start the video again. This is not meant to be a one blast and you get it all at the end. And remember, if you don't not writing the thing down, if you're not doing any work, you're not going to learn it. So get a piece of paper, pen out. We're going to do a little bit of revision to start off with. And I'm going to include all things from the astrophysics unit from this one. So if you're doing the astrophysics unit, then this is a good chance. There's some in here from the particle physics, and the nuclear physics as well, which you can do. So pick 2 or 3 of those, write everything you know about them, go and check your notes, and then do it again. It's the only way you're going to be able to do it. So there you go, depending on where you are, use all of those. It's really good practice because you need to keep all those memories coming back in. Okay, so once you've done that, come back to the video. And there is, that's the lesson that's gone on today. It just pops off the end there. Thermal capacity. It's basically going to be talking about the idea of thermal energy going in and out of a system and systems working. Usually gases we're dealing with here. But in terms of solids, we're going to be dealing with specific latent heat and specific heat capacity. That's with solids, liquids, and gases. So the thermal physics course generally deals with gases, but this first part is dealing with the amount of heat that individual substances can absorb and how much the temperature increases by, but also what happens when you change state. So we're going to start in solids, liquids, and gases, and then we're going to move on to gases later on. Just to run through these, to be able to define internal energy in terms of kinetic and potential energy, different materials have different thermal energy. To be able to apply delta Q or delta U, delta just means change. I'm going to interchangeably use delta Q and delta U as changes of energy. Delta Q tends to be energy transfer, delta U tends to be total internal energy. So there's quite a bit of variation. You'll see a bit of variation as you go through physics in general. And then we've got specific capacity as lowercase c, which I know is the speed of light as well, but generally they're not. They're easy to split apart in this. And to know that water is holding thermal energy. It's got one of the highest specific heat capacities of common materials anyway. And to know that delta Q, again, that's a change of energy, is mL. That's an L, which is mass and specific latent heat, with various things, various types of latent heats that come in there for a state change. Okay, so that's what we're going to be dealing with today. I've read it all out just to be crystal clear about what we're doing, so let's crack on. So, internal energy is a combination of these 2 factors. Kinetic energy, which is effectively the energy bound up in the movement of particles, and then potential energy, which is the bonding between particles. So if I've got a glass of water here, then I've got 2 things. I've got all the particles that are all jiggling around, and then there's going to be molecular attractive forces between them. So that's the 2 things that make up the internal energy of any particular substance. It doesn't have to be liquid, it could be solid, or gas. Now, first law of thermodynamics is all about work and heat. Now, the total internal energy of a system can change if I work on it. In other words, if I push it, literally working, force times distance. You can imagine it like I've got here, a piston. In other words, I'm squeezing the gas, I'm putting some energy into it, or I can let other particles hit the particles that are already there. In other words, I put one wall in contact with something that already has a very large amount of energy, like a hot wall, or putting a pan onto an oven. That's putting energy into a system. However, that system can transfer its energy away by letting it work. In other words, letting this gas expand the container it's in. It could be a balloon or it could be anything you like. And in this case, what's hidden behind my head is the idea of the system giving out energy as well, infrared radiation. So in other words, that heat, or by conduction as well, in other words, that heat, energy, the kinetic energy is being taken away somehow. So that's how we can change. Nothing too difficult there. Basically, I squeeze it, I heat it, I let it expand, or I let it radiate. That's basically the 4 scenarios. And this is how we boil it down in physics terms. So W we use for work, that's the squeezing or expanding. Q is the idea of heat added to the system. That's when something is contact with it. In other words, heat is put into the system. And these sorts of things can go in or they can go out. There's all variations of what you can do. So in the middle here, we've got the internal energy. If I work on the system, that adds energy. If I heat the system, that adds energy. If I give heat off, that means that's energy out, minus Q, and this goes down. And the work done by the system is minus W. Now, of course, we've got the law. This is what the law looks like. Delta U equals Q minus W. I'm not quite sure why they did it this way around, but nevertheless, let's go with this one. I'm sure the guys in 100 years ago had this one sorted out. So the change of energy is the amount of energy that is put into the system, the heat energy that's put into the system, minus the work that's done by the system. And I can only assume this takes a scenario that you're heating something up and it will expand. So therefore you put something hot next to it, so therefore the energy is being given by the particles, and then you let whatever it is, gas, let's say, expand. And so that's our first law. Now, A level, you don't have to do any calculations around this, it's just a qualitative approach. The only way that you would have to do a calculation is if it involves specific latent heat or specific heat capacity. That's how I interpret the specification anyway. So here we are, and this is in words. So changing in energy, heat added to the system, work done by the system. And just what's at the bottom there is just that little snippet out of the specification. And you can see, and there, just to really hammer it home, this is a qualitative treatment. In other words, internal energy is a balance of these two factors. Now, another way in which we can increase the internal energy by adding heat, so this would be the Q in this case, that would add this, is by adding heat to any sort of solid, or it could be liquid, but generally we're dealing with solids when we deal with air level. And this is a very simple equation, mass of the substance, whatever it is, could be iron, lead, water, whatever. C, which is specific capacity, joules per kilogram per Kelvin, and then the change in temperature. All specific capacity is the amount of energy required to heat 1 kilogram of a material by 1 degree Kelvin. And that's why I always do the 2-finger thing, separate fingers, because that's how you remind it. Specific capacity, 1 kilogram, 1 Kelvin, and that's how much energy is required. Yes, you may be asked to define it. I haven't seen an exam question where they do, but nevertheless, it's worth doing. It's a GCSE, so it's not too bad. And here's some typical specific heat capacities. And of course, in the A-level physics course, you have to get the idea of what these words are. It's in the specification. You have to know what these numbers are. And I always call it the daddy. It's the biggest one there, 4.2. There is another one that's slightly larger. These are elements, by the way, that are down. Well, there's a few alloys in there as well. But you can see water really does really very high. It's quite convenient, really, because we use it for our heating systems in our houses. And you can see that most of the materials, in this case these elements, take a lot less energy to increase their heat and their temperature. Here we are, some quick practice here. Calculate the amount of thermal energy required to raise the temperature of 3 kilograms of aluminium to 2080. Now, A-level, they're not going to give you this easy. What they'll do is they'll mess around with the units. So there we go, aluminium and copper at the top there. Ooh, look, it's kilojoules. That's what they'll do, and they'll maybe confuse you with Kelvin. They might just give you, say, 2 temperatures that are a long way apart. They might give you the mass in grams, like I've done here on B as well. In other words, you've got this idea that that they're messing around with things. Very rare you can have questions like this. Give those a try. Nothing too difficult there. So let's move on to specific latent heat. Now, specific latent heat, there needs to be an of after there, because specific latent heat is not a thing in itself. There's 2 positions where specific latent heat. It's the energy required to completely melt something, and the energy required to completely boil something. Or it could be the energy gained if you condense, or the energy gained if you are melting, for instance, or solidifying, freezing, whatever your word you want to use in this case. So in other words, it's the energy associated with breaking into molecular bonds or making into molecular bonds. Or what I like to say is the amount of energy that's contained within a bond. In other words, when a bond comes together, I can store potential energy within that bond. It takes energy to break that bond, but also you contain that bond. Energy is drawn into the system by making that bond. And that's how I always explain to my students about this weird thing about, oh, something's freezing and it's getting more energy. How the hell's that? Actually, the energy is going in to those bonds, and that potential energy is still there, ready to be broken. So that's how I'll see it. So in other words, that's where that energy goes. And the energy is stored within those bonds, and of course the energy is given out, and that's where you end up with these bonds coming through. So therefore you've got that there. Think of it as you can imagine as the heat's going somewhere else. So if you put something in the fridge, I'm pointing to my fridge. It's over there. Trust me. You put something in the fridge, of course, and it gets colder. You put something in the freezer, and you end up with all those intermolecular bonds bonding there. Imagine the heat is being taken out of the system. The kinetic energy is being taken out, and therefore you end up the kinetic energy has been taken out, and then when it goes from liquid to solid, the energy that's going out of the system is being taken out, and therefore you get these bonds being formed. Okay, so specific latent heat is all about energy required. I'm going to deal with it heating up because conceptually it's much easier. So in other words, I put heat in, things go up in temperature, and if you're dealing with specific heat capacity, this is where this is, kinetic energy. And then, of course, if energy keeps being supplied, that energy here comes in to the potential energy that's in there. In other words, your potential energy that's breaking those bonds between them. Then you start making them go faster, then you break the bonds again, and then they start going faster again. So, specific heat capacity, specific latent heat, specific heat capacity, specific latent heat, specific heat capacity. Or, to give them their proper names, specific heat capacity, specific latent heat of fusion, which is what that's called, and then specific heat capacity, and then specific latent heat of vaporization. And those are those two different types of specific latent heat, which are initiated at those two parts on there. And of course, they exist at the melting point and the boiling point, just like it says over here. Along here it says time, by the way, and we're assuming that as time goes by, heat is being constantly put into the system. So it's got a heater going on with a certain amount of power. And incidentally, exam questions do tend to just focus on power over time, and you have to work out the energy for the amount of time it takes. So you have to read off the time down here, multiply it by the power, then you've got the total amount of energy. That's generally where and so here we go. So fusion. So here's the definition of the two specific latent heats. So energy taken to completely melt 1 kilogram of any material. That is a specific latent heat of fusion. The specific latent heat of vaporization is the energy taken to completely boil 1 kilogram of whatever you've got. So specific, that's what specific means, by the way, is per kilogram. So if anything is specific, it means per kilogram. Please don't use that in normal life. It's one of those pedantic scientific things that please don't do that because that gives us scientists a bad name. Just when you're in a physics lab or talking to your teachers or just before a physics exam, you're allowed to use the word specific and pick people up on it. Specific means per kilogram. Don't mention it any other time. So specific latent heat of fusion is per kilogram for melting. Specific latent heat of vaporization is per kilogram when it's melting. Oh, it's boiling, sorry. Okay, here we go. So this is where's the energy going is a question up here. I'll come back to that in a second. But this is the equation, Q. Now, sometimes this is delta Q, sometimes it's delta U as well, because internal energy will be increasing or decreasing, depending on which way it's going. But basically, this is energy. It could be an E as well, if you want to. M, and this is a lowercase l, mass, and then just L, and then whichever it is. So if you're boiling something, it's the specific latent heat of vaporization. And if you're melting something, it's the specific latent heat of fusion. And these are the two equations. Now, each of these equations will be similar on the formula sheet, but they do require two different numbers. And if you look at the numbers of these ones here, you'll see again these are rough figures that you do need to know. You can see that specific latent heat of fusion on here is around the sort of 10,000-ish if it's joules per kilogram. And you can see specific latent heat of vaporization is usually a shade higher. Not a lot, but it's usually a little bit higher. I put the melting point and boiling points on there from here, and then said which are gases, liquids, and solids. Who worked that out? Why is water a liquid? At room temperature, of course. You have to get used to things boiling at very low temperatures, which is a really weird concept because most of the time we deal with water. So helium's boiling point is minus 268 degrees, 0.93 degrees C. And that's why it's a gas most of the time, because it's boiled. Copper has got a boiling point, although the idea of copper gas is a bit strange, but it won't boil until then. So getting your head around that idea is and then just to get a little visual into your head there, these things are all interchangeable, of course. You can go directly from solids to gases, called sublimation and deposition, but very rarely used in A level, and we don't have the specific latent heat for that particular part of it. So don't worry about that. We just deal with vaporization and fusion. Here's some questions for you. Here's some practice. These are very easy. All you have to do is just basically interpret the question. And notice the wording of the question is important when you're doing this. This is the most basic wording. Calculate the energy required to boil 5 kilograms of water. Skill from you required to realize this is the specific latent heat of vaporization. Realize it's 5 kilograms and just multiply it by this. So therefore you have to look at the data above. Water. Where's boiling? Water. There it is. There we go. And so there. Now, when we get into this, how much it will be melted by mass will be melted by heating ice with so much of this thermal energy. You can see I'm starting to clear on the language. And again, if you have this much liquid copper and heat it up to turn into gas, again, it's vaporization, specific latent heat vaporization again, and how much energy input is required to melt this. So in other words, you're never really given that. You have to be able to know which one to use. Nothing too difficult there. And again, when we're dealing with this, when we're dealing with this type of data, in other words, you're given a graph of a heating curve, in this case, cooling curves are just going the other way down. Explain where the energy is going in each area here. So in other words, your energy is going into increasing the speed, the kinetic energy of your particles here, the vibrational, where it's a solid. Here you're breaking the intermolecular bonds, and then you're increasing the kinetic energy once more, breaking intermolecular bonds, and then increasing the kinetic energy once more. Using section B, calculate the amount of ice used to produce the graph. So here we go. So just this one here. So it takes that amount of energy to be able to completely melt. Use the specific latent heat of water, which you'll be given to be able to do that. And then using section C, calculate the amount of ice to produce this graph here. And so there we go. So those two things should be exactly the same, and therefore you're using those different parts of it. This is specific latent heat of water, of course, and specific heat capacity of water, and this is specific latent heat of fusion of water, and that's how you could get those numbers there. Right, so this is where we start getting into really meaty stuff. This is a proper A-level question, which personally is one of the most complicated questions I have ever seen. So I'm jumping in at the deep end here because it's got everything, and I'm going to talk you through it. Mainly because the way I show it my students is that this conceptually, everything I've taught up to now is really very easy. There's nothing that difficult. Heat going in, heat coming out, gases expanding. Yeah, that's fine. You can know all that. Breaking bonds, making bonds, particles speeding up. Yeah, fine. Specific latent heat of fusion. Yeah, that's the one we're melting. Specific latent heat of vaporization. Yeah, that's the one where you're boiling it or condensing it. Every student's going to be able to get that conceptually if you've got this far in your education. What is hard is putting it into complex situations, and this is why it's advanced level. Molten lead at its melting temperature of 327 degrees C is poured into an iron mold where it solidifies. Okay, so it's just at its melting temperature, and then it solidifies. So it's right on it. So therefore, you must already think solidifies right. It's going from liquid to solid, so you're already thinking fusion. There's your first skill. Degree C should be shouting out to you, well, maybe it's a Kelvin thing, but we'll keep reading and find out. Temperature of the iron mold rises Right, it's a temperature rise, so it must be something to do with specific heat capacity. Iron mold, it's solid, so therefore it must be rises from 27 to 84 degrees C, at which the mole is in thermal equilibrium with the now solid lead. Right, so the lead has got changed from 327 solidified and then cooled down to 84. The iron mold has just risen from 27 to 84 degrees C. I'll just say that again because it's really important. It's solidified, then cooled down. That means that its energy transfer has gone into solidification, fusion, and in specific heat capacity as well. In other words, its temperature has changed. So you've got two forms, two parts of the energy that's been given up to the iron that's made it to that. Now, and they've used that word, it's given its energy to the iron. But the iron has only gone from 27 to 84, it hasn't done any melting or anything. So therefore, we've got a really good handle on the amount of energy that's changed. In other words, the amount of energy that's transferred in this case is 27 to 84 degrees C with the iron. That gives us an exact handle. And I haven't read a question yet. Mass of lead, great, we've got the mass. Specific latent heat fusion, mass of iron mole, specific capacity. Right, okay, let's just check units. Kilograms, yes. Yep, they're all fine. The only thing is, it looks like we're going to be fine with degrees C because it's just changes in temperature. Calculate the heat energy absorbed by the iron mold. Fine, specific heat capacity. So in which case we use this one, and we use this one here. Delta Q E equals MC delta theta. So get your mass. Now there's your mass of your iron mold. There's your specific heat capacity. You know the temperature difference, which is the difference between these two. So you should be getting the heat energy. Calculate the heat energy given out by the lead while it's changing state. Ah, great. So we're just dealing with it going from a solid to a liquid. So we know that it's at 327. We don't care about temperature when we're doing specific latent heats. It's just changing state. So all we need to look for the mass. Where's the mass? There it is. Okay, and there's specific latent heat fusion. All you do is multiply those two bad boys together, and you've got the heat energy given out. Right, now this number here, of course, will be significantly smaller than this number here, because the difference between these two numbers is how much energy the lead has given to the iron for it to be able to be cooled down from 327 to 84, because it hasn't changed temperature yet. Specific capacity of lead. Notice there is absolutely no clues whatsoever given. The key is always thinking about two different energies. Energy of it solidifying, energy of it cooling down or heating up. Energy of it heating up, energy of it for it boiling. Those are the two things that are always here. So all I have to do here is take those two energies away from each other. So take the big one away from the small one. That will give me the energy that is being given out by the lead or absorbed by the iron, depending on which way you're looking at. What am I dealing with? Right, so let's think. If there's a difference in temperature, it's the heat capacity of the lead I'm dealing with, isn't it? So therefore, I need the mass of the lead, I need the energy difference, and I need the temperature change. What's the temperature change? It goes from 327 to 84. That's all I've got, and that's all I need. So it's one equation. The hard bit was working out the difference between these two. State one reason why the answer to part 1C is only approximation, because the heat's going everywhere else. This is not a sealed system. Okay, it's just giving out to the surroundings. The answers are coming here. I haven't done any numerical stuff there because, frankly, the numbers change. What you need to do is get the concept. Do the question, satisfy yourself. The answers are coming up in 3, 2. Okay, there you go. There's your specific heat capacity, specific latent heat. That's the difference. As you can see, the numbers between those two. And then you end up with a specific capacity of 154, which makes sense. You remember I said in the hundreds, water's in the thousands, but it's one. Heat loss, job done. Okay, next one. Very similar question. In an experiment to measure the temperature of a flame of a Bunsen burner, a lump of copper of mass of that is heated up by a flame for several minutes. The copper is then transferred quickly to a beaker of water, and then containing that much water, and the temperature rises. So you can see what's going on. Okay, you're heating up the copper energy has been absorbed, it's getting hotter, then you put it into the water, you measure the temperature increase of the water, and then you can try and get the idea of what the temperature of the flame is from that. Yeah, good idea. Okay, temperature of the water rises from 15 to 35. Calculate the thermal energy gained by the water. Straightforward, specific capacity, job done. Calculate the temperature reached by the copper flame, assuming no heat is lost when the copper is transferred. So therefore, what you're dealing with here, you're dealing with how much you want the temperature difference, basically, of the copper. So therefore, take the amount of energy, transfer it to get the copper specific capacity of the copper. So you've got your energy that's you already know it. You know the mass of the copper because it's there, and you want to calculate the temperature change. So therefore, work out the temperature change from that, assuming it's from room temperature. Okay, that's the temperature change. But when the lump of copper entered the water, some of the water turned to steam. Did it now? Specific latent heat of vaporization of steam is that megajoules. What further measurement do you need to be made to calculate the energy produced? Steam, of course, you need to work out how much steam is produced. So therefore, if you've got that, so what further measurement we need to calculate the energy used to produce this steam? In other words, what's the mass of our steam? What's the mass loss of our steam in this case? Describe how this further measurement should be used. Accurate flame temperature. So in other words, we've got to make sure we capture all of that liquid. So how do we measure the mass of the water? So you can measure the mass difference when it gives off. Without further calculation, describe how this further measurement should be used to a more accurate value to basically calculate the thermal specific latent heat of your so the boiling specific latent heat of vaporization of the water, and then that'll give you the energy that's gone into making steam as well as the temperature increase. Much more accurate value. Nice question. And there are sorry I didn't warn you. There are the answers that are coming up there. Okay, there you go.